Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 44 of this seminar. Today we have two excellent speakers, Lionel Rosier and Ana Silvestri. Introducing Lionel Rosier, we have to Professor Roberto Capistrano. Thank you, Roberto. You can start.
Okay, thank you, Juan. Thank you, everybody. It's a pleasure for me, at least for me, introduce Professor Lionel Rosier. Professor Lionel was my advisor in my PhD. Let me give some information about Lionel. Professor Lionel is graduated in mathematics from the École Normale Supérieure de Caen in 90, and he received his PhD there in 93, okay, under supervision of Jean-Michel Coron. After that, he's take habilitation à diriger de recherche in 99, okay, in the University of Paris Sud in Marseille. Okay, about his trajectory, Lionel was associate professor at the École Normale Supérieure de Caen and the Université de Paris Sud. Also, he was professor at the Université de Lorraine and Mines Paris Tech. He is currently professor at Université du Littoral. Okay. Lionel Rosier has 6 PhD students in collaboration with different universities, Brazil, Chile, and of course, France. His research is interested in including Lyapunov theory, control of PDEs, fluid mechanics, inverse problems. And Lionel has more than 75 articles in respected international journal and more than 1,500 citations in MathSciNet and 5,000 citations in Google School. As we can see, Lionel has a brilliant papers and book. I will at least talk about 4 of them. Okay, for me, my point of view, is beautiful works. The first one is a book of Lyapunov function and stability control theory, in control theory with Bicciotti. Okay, it's an interesting book. The other one is 3 papers, interesting papers. Homogeneous Lyapunov function for homogeneous continuous vector fields in system and control letters. For me, a more interesting work that I see in my life is exactly boundary controllability for the KdV equations. In this paper, Lionel presents a critical set phenomenon for these specific systems. It's a paper in 97 of Science. And another interesting paper, in my point of view, in the trajectory of Lionel, is a relation between continuous time varying and discontinuous feedback stabilization with Coron. Okay, this is just a small sample of Professor Lionel's brilliant career. Well, today Lionel will give us a lecture with the lecture is numerical control of the wave equation by a directly approach. And Lionel, thank you very much for accepting this invitation. It's for me, at least, a pleasure to introduce you. Thank you.
Okay. Thank you so much, Roberto, for this very nice introduction. And also, I would like to thank the organizer for their kind invitation. And so, as Roberto said, so I will talk about numerics for the control problem of a wave equation. And I will use some direct approach, which is, to my opinion, new in this problem, for this kind of problems. So, okay. So I will talk about joint work with Marcelo Cavalcanti and Valeria Cavalcanti, both from Universidade Estadual de Maringá, and with Carole Rosier from Université du Littoral Cotopale in Calais, in France. Actually, so I will talk about 2 works, 2 papers. So the second part will be devoted to the control of the subilinear wave equation, that is a nonlinear wave equation in dimension 1. And so we will investigate some numerical aspects for that. And actually, it is a joint work with Marcelo, Valeria, and Carole. And depending on the time I have, I will talk about a more recent work about the control of the linear wave equation in dimension 3 by using Huygens principle, and it is a joint work with Carole Rosier. So this is the plan of my talk. So it's mainly two works, one in dimension 1, but for semi-linear wave equation, and another one for the linear wave equation in dimension 3. And so we are interested in numerics for that. So a very small introduction about the control of the wave equation. So we are concerned with here with a numerical investigation of the null controllability of the linear or the nonlinear wave equation. So I have written a nonlinear wave equation in dimension 1, ytt minus yxx equal f of y. And so I remind you what is the problem of the controllabilities. You assume given some initial data, so xi0 and xi1, and so you will apply some control here at the boundary. So it will be at x equal 1, and at x equals 0, you will take homogeneous boundary condition, and you want that at the final time you are at rest. So that is y and yt are 0. This is a classical null controllability of the wave equation. Okay, so this problem has been investigated by many people. Maybe one of the first contributions to the subject is due to David Russell in 1973. Also, you have works by Lyons, by Bardos-Lebel-Roche. So Bardos-Lebel-Roche obtained, in some sense, the definitive result in dimension n for a very general open set. This is so for the linear equation. And when you look at the sublinear wave equations, to my best knowledge, the first contribution is due to Deman-Lebeau and Zhuo in 2003. So they obtained null controllability or exact controllability for nonlinear wave equation in dimension n. So this is for the theoretical result. But it turns that to pass to the numerical result is not obvious at all. Actually, you have to work. And it was first investigated by Glowinski, Lee, and Lyons in 1990, so more than 30 years ago. And also after by many people, so H-Lebeau, Zhuo, Munch, Castro-Miku, and many others that I did not refer here. And so all this method actually mimic what is done at the theoretical level. So they use the HUM, the so-called Hilbert uniqueness method introduced by Jacques Lyons. And it turns that when you do that, actually you have some phenomenon, some new phenomenon, which is bad. So you have the emergence of spurious high frequencies, and it's bad. So you don't have this problem actually at the continuous level, and they appears. When you do numerics, for instance, if we use a finite element or finite difference, you have some problems. And so people have to introduce some remedies, so some new things, ingredients to balance these bad effects. So, for instance, H and Lebeau use multi-grid method, but you can as well use as Zhuo filtering. You can also introduce viscosity inside. Right? So yeah, people use many methods to balance this problem of the emergence of spurious high frequencies. Okay, and so the idea of this work is to see if we can attack the problem, but without this treatment, this numerical treatment actually. So if we can attack the problem directly, for instance, without filtering or viscosity. And this is what we will do first in dimension 1. So instead of HUM, we will use a direct approach to control the linearized equation first. And after, okay, we will have some result for the nonlinear equation. And we don't need any filtering. This is what is important in this work. So the first part, so is the joint work with Marcelo, Valeria, Carola. So that the control of the sublinear wave equation, and it was presented in some conference, Decode, and it will appear in the proceeding of this conference soon, very soon. So I need to introduce a few notation. So L2 of X, so I write X to mean that I deal with a space in the X variable. So it's a L2 of 0, 1. Our domain will be 0, 1 in dimension 1. And so H1X is a sublet space for the same interval 0, 1. And when I write T, it means that it will be some interval for the time. So it will be H1 of 0 capital T. And actually here, here t will be 2. So we have to introduce the two spaces. The space in blue is a classical space for the well-posedness of the wave equation with a homogeneous Dirichlet boundary condition. I mean, you assume that the solution is 0 at x equals 0 and x equals 1. So it's a space H0. And the space H in red corresponds to the fact that, okay, at 0, you are still 0 because there is no control, but at x equals 1, you have a control, so you cannot say what is the value. And so it's a space appropriate for the control problem. And so both spaces are endowed with the norm YZH, which is defined in the slide. And so it's a classical norm, okay, for this space. And for the nonlinear part, so we have to introduce some function f in W1 infinity of minus delta 0, when delta 0 is a small positive number, and you will assume that f is 0 at 0, and that the L infinity norm of f prime is less than a constant, strictly less than 1/2. But it can be very general. Okay, so the first thing to do is to deal with a linear problem. And so you have to construct some operator, some boundary operator to solve the problem. So here I consider the exact contrariety. So I can start from 0, 0. So y and yt are 0 at time 0. And I want to reach at time capital T the states xi0t and xi1t. So I can maybe use this. So I want to reach this state, time capital T. So at 0, you don't have any control. And at x equals 1, you apply the control ht. Okay, so which depends on the final state you want to reach by some operator lambda. And so in the classical literature, lambda is given by HUM. Okay, but here and so they built the control according to this way to proceed. And okay, we will see that actually lambda can be explicit in a very simple way. And so we will not use HUM for that. So I describe the Picard iteration scheme. So we want to have at the numerical level some exact controllability for the nonlinear wave equation. I remind you that at the theoretical level, we know that it is controllable. It's not for more than 20 years, but the problem is to obtain some result at the numerical level and to justify actually that we have a good convergence. We want to obtain an error estimate. So how to proceed? So this is the schemes that we use. So we start from some initial data T0 and T1 in the space H0. So that I described just before. And so we start with two boundary control, H0 and delta H0 that are 0 to begin with, okay? So this is to initiate the loop, the induction. So assume that n is larger than 1 and that each hn minus 1 and delta h minus 1, n minus 1 have been constructed at the previous step, and that both are in the space h10. So we set hn is hn minus 1 plus this guy. So hn will be the control at the rank n. So it is the control at the previous step, but with some correction. So at each step, we add some correction. Okay, this is the idea. So how to construct the correction as the next step? So starting from this control, what we do first is that we solve this boundary value problem. So you have some initial value and you have your boundary control, boundary value, and you solve this sublinear wave equation. So you can make it, you obtain solution y1. Okay, so now it turns out, of course, the final value of your solution is not necessarily 0, or it could be, but only by chance. Okay, so it will not be 0. So we have to modify it to make some correction. And at this level, we use the control operator for the linear equation that we denote by lambda, and it was introduced before. Okay, so this is a correction, delta hn. And now you solve the problem with this small correction. And so now you start from 0 and you apply this control at x equals 1. and you solve the linear wave equation. Okay, you solve the linear wave equation, you do the sum. So you obtain now a solution y2, and you do the sum of y1 and y2, and you obtain yn. Okay, you obtain yn. So this is the solution at the rank n. So what is the system satisfied by yn? So maybe we can begin with the initial condition and the final condition. So the initial condition will be x0, x1 because it corresponds to this one, and here it is 0. The final condition will be 0 precisely because we had this correction to the control. Okay, and so this is the new control. It will be hn plus 1. Okay, and now what is the equation satisfied by yn? So it is not a sublinear wave equation because here we have this term, which is not f of yn, it is just f of y1n. Okay, so this thing is not exactly the solution of our null contrariety problem for the sublinear wave equation because okay, we have y1 instead of y. But it's not a concern because we can pass to the limit, and at the limit, so okay, we obtain this result. Okay, so the main result is the following: you choose t equal 2, so you can pick delta small n house, epsilon between 0 and 1, and c positive, such that if the initial data x0 and x1 is small n house, less than delta, then you have this convergence estimate. So you see in red that y1 will converge where y towards y, and the same for the derivative. y1t will converge where yt. And what is y? Y is a solution of the null contrariety problem for the sublinear wave equation. So you start from this state, and by using a convenient control, you arrive to 0 as you want. But so the solution y1n that you construct by your picker scheme will converge to the solution of this guy. Okay, and also you have a convergence of the control hn and also of this guy. Okay, of the perturbation, and you have a very fast convergence because it is like this. Okay, it converges in a fast way. Well, so this is the result. So now we are left with the construction, the numerical construction of yn and hn. So how do we do? So we have used Chebyshev collocation method. So maybe it's not familiar to people. So I will just remind something. So the idea is to use the points that are given by the so-called Chebyshev points that are given this way. And so the mesh of the point xj is not uniform. Actually, they cluster as a boundary. So you have more points at x equal -1 and x equal 1. And why is it interesting? So, of course, in our wave equation, you have a second derivative in space, and so you have to compute it. Of course, you could use a finite difference, but it's not so good. It turns that by using this point, you can have at low cost, at low computational cost, you can obtain estimate of the derivative. So this is what I would like to explain to you. So you consider the Lagrange polynomial function p that interpolate your function u at the Chebyshev point. So it's a polynomial function of a degree at most n. And you take the derivative of this polynomial function at each of the point. Okay. It turns that this derivative gives a very, very good approximation of the derivative of u. First, you can compute it in some systematic way because if you look at the derivative, it can be expressed as in a linear way in terms of u. And I remind you that u is the value of u at the Chebyshev point. So first, you can make it in a very fast way. And it turns that you have this very important estimate. So the difference between the derivative of the Lagrange polynomial function and the derivative of the function is like this, where k larger than 1. And so it turns that in practice, when you take n equal 20, so only 20 points, and you have some estimate of this guy less than 10 to the -10, which is very, very small. And of course, this something that you cannot obtain with finite difference with only 20 points, and you need a lot of points to, so something like a 10 to the 10, I guess, to obtain this kind of estimate with finite difference. So it's much better. But okay, your function has to be analytic for that. Okay, this is explained in the very classical book. So for instance, the book of Canuto, Husseini, Quarteroni, Zhang, or the book by Trevenpan. Okay, so now you have that. So what is the scheme we use? So we have to use both linear wave equation and sublinear wave equation. So after a change of variable, is it to see that you just have to deal with this kind of problem. So it's a sublinear wave equation on the interval -1, 1. I take this interval because it is more convenient to deal with the Chebyshev part, or just a numerical facility. And so the scheme is the following. So for the time, you just use a leapfrog formula in T, so the classical thing that everybody do, even with finite difference. But for the space derivative, we don't use finite difference. We use this thing. So the estimate of the derivative given by the previous slide, by the collocation method. Okay? This is what we do. So okay, this is the scheme what we use to do the computation. Okay. So now how to build the linear control problem, because we have, I say that there is a control lambda, linear control operator lambda. So how to build it at the numerical level. So we don't use HUM, we don't do that. Actually, you can have explicit formula. And this explicit formula actually comes from the fact that if you use this transparent boundary condition for the wave equation, you obtain the finite time stability. So the solution is 0 after a finite time. Okay, so you use this very nice property, and you solve your wave equation by using Riemann invariant. I have to skip the detail, but this is the way I proceed to write the programs. Okay, so use Riemann invariant. And so with Riemann invariant, you just have this relation by just integration. And so you are left with the numerical approximation of this integral. And the way we do that is to use actually the trapezoidal rule. It's very simple. And so you can compute it in a very simple way. So let us look now at the simulation. So first simulation, I have considered f of y is c. So f of u is cu squared, so it's a quadratic term. These are the initial data. So I did the simulation with c equals 0, which corresponds to the linear case, and c equals 4, which corresponds to the nonlinear case. And okay, for the data, so we use 5 iterations. So in the Picard scheme, we have 5 iterations, and we took 200 Chebyshev points. And this is the interval for the time. Okay. Okay. And so we are able also to give some estimate of the infinity norm of our function. And with this data, we obtain some relative error, which is less than 10 to the -2, which is very good. Okay. So this is the simulation. So we are for these two. So it is a simulation for c equals 0. So it is the linear part. And this is the simulation for c equals 4. Okay. So this is x between 0 and 1. So at x equals 0, so everything is 0 because you have homogeneous boundary condition. And here you have the control. And the control is also displayed in this curve. Okay, so this control is this one, and this control is this one. So what you see that at the final time, everything is 0, so it's okay. And so the trajectory looks very similar. But actually, when you look at the control, you see that the control is not exactly the same. So this is the control from the non-linear part. So it's different from the control for the linear part, okay? And why? Because you have to balance the non-linear term. And so because of the non-linear term, you have to change the control. Okay, it's just what I see, okay? So for another function, so you can proceed slightly differently. Actually, you can use the fact that the function f is odd, that it was not possible to do that before. So I will skip the detail, but so look at the function f of u equals cu to the 3. So we test our scheme for c between -2 and 1.8, and it works well. It works very well with the same kind of iteration, 5 iteration in the speaker scheme, so it's okay. For c equal 2, we obtain some blow up actually. So whatever the controls you put at the right, you have a blow up. Oh, this is bad. And when c is less than -3, we don't have a blow up, but we are not able to reach your target. Okay, so it's different. So the simulation, so when c equal 1.5, so you see that it works well. So now the simulation is done between -1 and 1. And actually you have just to keep this part for your problem, initial problem, original problem, okay? I remind you that we consider odd function, okay? So at x equals 0, this is 0, okay? Okay. So another value when c is -4, so as I said to you, you don't have blow up, but at the final time, you don't reach 0. Okay, it's bad. And so another nonlinear term. So f of u is c sinus of u. So it was a question raised by Enriquez as well. So we know from at the theoretical level that we can control the system to 0, whatever the value of c. But with our scheme, when c is 6, okay, we are not able to reach 0. Of course, when c is small, our scheme works. Okay, so this was for the first part. How many time do I have, Roberto? 15?
No, as 20 minutes. It's okay.
20? So, really?
15, 20 minutes. Okay.
Okay. So I will describe some work which is more recent by done by myself and Carol. So we look at the numerical control of the linear wave equation in dimension 3 for the moment for a very simple geometry, and we use Huygens principle. Okay. So what is Huygens principle? So you have to go back to the classical way to solve the wave equation, like it is explained in the classical textbook by Evans. And so you have the solution by spherical means, which is very classical. Maybe you teach it, by the way. So you obtain what is the so-called Kirchhoff formula. And from Kirchhoff formula, you obtain in dimension 3, not in dimension 2. It's not true in dimension 2, but it is true in dimension 3. You have this principle. So if you consider a smooth solution of the wave equation in dimension 3 for the space, and starting from V0 and V1, if at some x you have that V0, V1, and the gradient of V0 is 0, provided that at y, for y distant from x of t, then v is 0 at x and t. So t, so if we restrict to positive time, so t is a radius of the sphere, and you assume that on the sphere centered at x, so v0, v1, the gradient of 0 is 0. So in that case, v should be 0 at x and time t. Okay. So this is the strong Huygens principle, and it's very important in control because so if you start with, if you assume that the data v0 and v1 are supported in a compact set K, and if the diameter, if t is large, the time capital T is larger than the diameter of K, then you can prove that v is 0 when for x in K and t, which is non-negative, and actually put larger than t, capital T, and just a consequence of this. So you obtain the null controllability, but only on K for large T. Okay. So okay, so it was the starting point from the design of a control method for the wave equation in dimension 3. So the idea is the following. So assume that you want to work in this small set omega, and so you split the boundary into two parts. You have gamma 0. The part on which you want to, you can apply control. And this part here, gamma minus gamma 0 is the part where you take homogeneous boundary conditions. So there is no control. The solution is 0 here, okay? Okay, so how to control it? So the idea is to plug this part into some surface S that will divide the R3 into two open set. So two parts. So you have omega 1, which is unbounded, and omega 2, which is here. Okay. So this is a splitting. Okay. So S is contain this part where you have no control. So this is this big, and R3 minus S, you have omega 1 and omega 2. Okay, and both are unbounded. Okay. So I remind you that gamma 0 is the part where you apply the control. Okay. And now you have to assume that you have to be careful with that. You assume that you have a sort of Huygens principle, not on R3, but only in this domain, which is embedded, and which takes the following form. So if you have a solution of the wave equation, which is 0 on S, and with initial data that are supported in some compact set K, then the solution has to be 0 in K for T, which is large enough. So it's sort of extension of Huygens principle, but on omega 1. This is not true for any omega 1. So if you have triple way, so if you have a form like this, or I didn't do the picture, but if you have a work like this, you can have a triple way, and you will have not, this property will not be satisfied. Okay, so you have, I don't say that it does exist for any set, because actually we cannot control the wave equation in any set. You have to make some assumption, some geometric assumption, but okay, I assume that this is true. For the numerics, actually, we have to introduce some intermediate open set, which is denoted by at of omega here, and which is finite because, of course, for the numerics, you always have to work on a bounded set. Okay, so now if you assume given U0 and U1 that are in the classical space for the wave equation, so you make extension by 0 on omega 1, and you solve actually the problem V in omega 1. So you solve this problem here, okay? And after you take the restriction. And I say that the restriction, so U of V and G is the restriction of V to the boundary where you have the control. This restriction will solve this problem, okay? So it will solve your control problem. Okay, so in practice, as I said to you, we cannot work on some unbounded domain. It's not possible to use numerics. So the idea is to use a bounded domain omega hat, which is convenient for the thing. What you have to impose that when you have wave originating from this set, when they arrive to this set, you will have bonds, of course, but you ask that the bonds will not arrive to this set in time capital T. Okay, so this is a way to choose this set. So this is a program, actually. It is a program, and we are able to use this program on what I call a cuboid, which is actually the product of 3 intervals, which is a natural extension of what we did in dimension 1. Okay, so this is a product on 3 intervals, and for this, in dimension 3, we can make it. We can realize also this program. So this is a set omega. So we assume that we control on this set. So we have 3 faces. So x1 equal L1, x2 equal L2, and x3 equal L3. So this is the part on which you put the control. So 3 faces, and the other part is the part of the boundary where your solution should be 0. So what you do, so you expand U0 and U1 as a Fourier series of sinus function. So you can make it, of course, and assuming that U0 is in L2 and U1 in H-1, you have this condition for the Fourier coefficient. And actually, it's a way to see what is the regularity of U0 and U1. So you can use this operator minus Laplacian with the classical Dirichlet boundary condition. Okay, so this is the domain of your operator. And U0 and U1 will be in this set. Where you have some power of this operator, if and only if this condition is satisfied by the Fourier coefficient. Next, we introduce some cutoff function of rho, which is 1 for z less than 1 in absolute value, and which is 0 when c is larger than 1 plus epsilon. Okay, so from U0, so you introduce 2 new states, V0 and V1. Actually, that this state will be defined on R3. So you recognize the same series here, but actually you look at a function which is both periodic and odd in x1, in x2, and x3. And so you leave the initial domain in some sense, and you multiply by this cutoff C, which is defined thanks to the cutoff function rho. And okay, so capital L, we choose a number capital L, which is larger than this quantity. And we use as a box, the box to do the numerics, hat omega, which is minus L to the 3. Okay, so what we will do, so we will solve the wave equation in this cube with the L, which is much larger than L1, L2, L3. Okay, so we'll do the computation in this thing. And actually the regularity of V0, V1 is related to those of the U0 and U1. You have the same regularity. Okay, so now I arrive to the result. You can see that V is odd in X1, X2, X3, and thanks to that property, as it is odd, it has to vanish when X1 is 0, or X1 is 2, or X2 is 0, or X3 is 0. So you have that on the face where you don't have control, you have indeed the directly homogeneous boundary conditions that are satisfied. So what you do next, so, okay, you expand again as a Fourier series, but be careful, it's not L1 here, it's LL, so because you work in the big box, okay? And of course, everybody knows that you have some explicit solution, formula for the solution of V on the big box, which is given this way, so it's a classical exercise that you give to students, okay? And now you just have to take the restriction to the original domain, and you solve actually the null contrariety problem for this time. And actually, this time is almost sharp. So when epsilon is 0, it is a sharp time. Okay, so this is a sharp time for this configuration of the control. So we obtain a small theorem like this, which tells you that okay, if the initial data is sufficiently regular, and if you replace this infinity series by a finite sum, that is, you look at partial sum, and it is denoted by Vn. So you limit the frequency to K1, K2, and K3 less than n. Then, okay, the difference between the solution of the this system, the complete wave equation, and the partial sum corresponding to this frequency, the difference is given this way. So you have the regularity of U0 and U1, which appears in this estimate, but also you have this thing. So if S is larger than R, so it decreases in a fast way. So when n tends to infinity, it tends to 0. This is what we want, of course. So the idea is the following. You have explicit formula, so we consider this partial sum, and it will give us some approximation of the control problem, the solution of the control problem. Okay. So, so I just show you now the simulation. So we did the simulation with this. So this is the box. How many times? How many? 5 minutes? It's okay?
It's okay. You have 10 minutes, you know. You have time.
So okay. So for me, it's complete now. So this is the original box, small one. So 0, 1/2 to the 3. And the big box will be this one, okay? This is out of H, okay? So this is the value of L1, L2, L3, it's 1/2, and L is capital, it's P. This is the initial data. So U0 is some Gaussian concentrated at 1,4, 1,4, 1,4. So we need this so that the solution will be 0 at the boundary. We need something like that. So we want to have a lot of regularity, not to have problem. Okay, and we take U1 is 0, and actually we pick a cutoff function which is not smooth. Well, we could do the smooth function as well, but just to do the things in a quick way. And what is important is that, okay, we can pick n equals 50. So what is important is, of course, to do this thing. Sorry. Okay, we have to compute this partial series with this condition. But you have 3 variables, K1, K2, K3. So we have 50 to the 3 Fourier coefficient to compute. It's a big deal because, and each Fourier coefficient is some integral on a cube, okay? So it's okay, you need a lot of computation to do, even for one coefficient, one Fourier coefficient, because it's some integral on a cube, okay? Okay, so let us have a look at the simulation. Of course, it's difficult to represent because it depends on x1, x2, x3, okay, and type. Okay, so what we did, we do section. So we assume that x3 is 1/4, okay, just to see what happened. And we did also section with 1/8 and so on. Okay. Well, so this is the original Gaussian. And so we do the computation of the partial sum, so with Fourier, and we see, okay, waves that go away from the domain. And this is the important part of our domain. So between, for x1 between 0 and 1/2, and x2 between 0 and 1/2, and it's okay, because here is 0, the solution is 0. This is what we see. So, okay, the wave leaves the domain, and at the final time, it's okay. We have the exact contrariety, the new contrariety. And this is also the representation of the L infinity norm in the domain 0, 1/2 to the 3. So we make some computation with a lot of points. And okay, this is what we see. We start from 1. Okay, it reaches 0, but not in the classical way. It's not monotonous. Okay. So I conclude now. So we obtain a very good approximated solution for the seminar wave equation in dimension 1 by using a Picard iterative scheme, and we don't need to introduce a filtering or viscosity. And so the idea is that for the linear wave equation, we use transparent boundary condition, and for the method, the numerical method, we use pseudo-spectral collocation method to compute the derivative in space. So we did the extension dimension 3 by using Huygens principle. And so for the next direction of research, so we have to do the numerical analysis. Also deal with the linear wave equation with variable coefficient, we know how to make it. And also deal with the linear wave equation in some arbitrary bounded domain in R3. And actually it is a joint in progress with my colleague Antoine Benoit and my PhD student Romain Loyer at Calais. Thank you, that's all.
Thank you very much, Lionel, for this nice presentation. Well, I will open for the questions for the audience, some comments or questions. The audience is open and everybody can some comments, questions. Let's see in the chat. Okay, I have a curiosity. As you know, I'm not familiar in this kind of problem, but in the approximation, you put a error in the control, right? In the first work, in the first problem.
Yes, so
that's why in the first problem you put the previous yes, the first one. Okay, pass for the next one. Here in the the previous one, the page 8. Previous one. Here in the last part, you put your control plus a error multiplied by a control, right? Why? Just a curiosity. Why this is important? You introduce this part of it in your problem, the control here, for example. Of course, if
you mean this one or this one? What is your question?
The second one, the last one, when you put together.
This is a correction. So I told you, I told you in the talk, it is a correction because if you look just as a solution of this system at the final time, you will not have that. There is no chance. So you make a correction.
Okay.
You make a correction. So you replace this guy by this guy. Okay. So, so you make a small correction, and thanks to this, now you have that.
Okay.
And now you lost this equation, and now you have this equation, which is not exactly a seminar equation, but it's not a concern because everything converges well, and so it's okay.
So okay, and of course, maybe this kind of process can be applied in another PDs, right?
Yes.
No.
So this scheme, yes, actually, it's more or less the way it's. You know that Picard scheme is a way to prove the contraction principle. So in some sense, it's a new proof of the, because actually we obtain again. We obtain again that this thing is non-controllable. It's a byproduct. Okay.
Oh, okay.
So it could work to other question. Now, for the rest of the work, I'm not sure that you can make it. So I mean, for the heat equation, you will not able to control to build the control operator the same way. And it will be difficult, more different actually.
Oh, okay, okay. And about the explicit time there and the last work you prove, you show me, please. This time, the previous one.
It's optimize the sharp one.
Okay, okay. This is because the method or not, Lionel?
I think we will obtain the sharp one. For very general domain, it's not. I cannot say it exactly. No, maybe we don't have it for a general domain, but for this domain, yes. For this domain, for sure. But for a more general domain, we will obtain the new contrariety for time larger than the time given by the theory of Pardos-Lebeau-Roche, I guess.
Okay, okay. Okay, more questions or comments?
I have one question.
Okay,
Yes,
please.
Lionel, the choice that you have made for the boundary conditions, namely the transparent boundary conditions, is this some related with some physical meaning that you want to give to your equations? And is there some relation, for instance, with the do nothing boundary conditions that we sometimes use in fluid flow?
Difficult to say. Now, the idea for the transparent boundary condition is to leave the wave, leave the domain without bounds. This is to avoid bounds at any aspect, to avoid the bounds. Okay, so they leave and they don't see in some sense the boundary condition. This is the way I see the thing. And actually, this thing was introduced by Maeda in the 70s. And he introduced that for the 70s in dimension 1, although he made something in dimension 3. And I know there is a literature for the numerics because people want to do the numerics on box, and they want to avoid the bonds. So they want the wave to go at infinity. So people interested in numerics use these kind of things. Okay. But I don't know so much the boundary condition you talk about for the fluid mechanics. Maybe it's related, maybe.
Yeah, I think it's a similar idea. We also want to truncate some domain, and the flow has to leave the domain in such a way, for instance, that you don't see backflow, for instance. So I think it's something similar from the physical point of view. Of course, the context is different, but
yes, I think this is something interesting. So actually, even for the control, and for that, okay, we can skip completely HUM, and it's good for that.
Thank you.
You're welcome.
Lionel, more questions or comments? We have some times. Okay, if not, let's say thank you again for Lionel. Thank you, Lionel, for this nice talk.
For the invitation. So I don't share now. I have to stop. Okay, sharing. Okay.
Thank you, Roberto, and thank you a lot, Professor Lionel Rosier, for your amazing talk.